Hello everyone. In this week's experiment, we're gonna learn how to reduce vanillin and get vanillin alcohol with sodium borohydride. So the purpose of our experiment this week to perform a sodium borohydride reduction of an aldehyde to produce an alcohol. The product will be characterized by measuring its melting point. And if you do this experiment in the lab, you will find it is very fragrant full lab, and you will feel and you are surrounded by vanilla. Okay, it's a beautiful, a nice aroma that you will be experiencing in the lab. So the learning objectives for this lab going to be safely work with reducing agent sodium borohydride and adjust the pH of a reaction mixture to allow the solid to precipitate form. Isolate the solid product via vacuum filtration and characterize the solid via melting point determination. And I urge all of you to read this background and discussion because it has a lot of theory behind this experiment, and this will also help you to write your discussion. Okay, and it also talk about oxidation reduction. And if you recall from your general chemistry, which all of you have passed the general chemistry, remember we learn about oxidation and reduction. We learn about this term oil rig. Oxidation is loss of electrons and reduction is gaining. And the common example that we know for the oxidation and reduction, sodium is a metal. If you lose an electron, it will become sodium plus 1 by losing electrons. So if you have less electron density, that will create a positive charge, and we call it as oxidation. And then the reduction is gaining an electron. The electron that sodium lost, chlorine gains it. Chlorine now becomes Cl minus 1. And this is the reduction. And the first one is the oxidation. So in the reduction reaction, what do you think about the electron density? Electron density surrounding the atom that we consider increases. And in oxidation, electron density decreases. So in organic chemistry, we normally don't give the numbers as to whether it is plus 1, minus 1, but we're going to look at what happened to the electron density on carbon, because it's mostly the elements attached to carbon either loses, one atom loses, another atom comes in. So we're going to look at what happened to the electron density on the carbon to see whether it is an oxidation or a reduction. Okay. So in organic chemistry, we can see what is happening. Let's say we have an aldehyde. Let's take this example. And then we say in the presence of sodium borohydride, we reduce it to give you an alcohol like that. Now we are looking at the carbon, that the oxidation or the reduction going to take place here on this carbon. Normally electron density of carbon, the number for the not density, what's the number? Electronegativity. Carbon electronegativity is 2.5 carbon, and hydrogen 2.1, and oxygen electronegativity 3.5. Okay, now in the first one over here, carbon is attached to oxygen with a double bond, and it has only one hydrogen. So having electronegative atom attached to carbon, what do you think? Does carbon has more electron density on carbon? Well, we have to compare it. Let's compare it with the alcohol that it's going to form. Now here we have a carbon here. That carbon has 2 hydrogens and 1 oxygen, whereas your starting aldehyde has 1 hydrogen and double bonded oxygen. Which one do you think has more electron density? Carbon with double bonded oxygen or carbon with 2 hydrogens and 1 singly bonded oxygen? So with the pi bond in the aldehyde, it is also you can have the resonance forms like that, O minus plus hydrogen, right? Once the pi bond goes to oxygen, but you cannot draw that resonance structure for the alcohol. So, and also it has only one hydrogen. So which one do you think carbon will have higher electron density, with one hydrogen and one oxygen atom, or two hydrogens and one oxygen atom? Since alcohol hydrogens, there are two of those, okay, so this carbon on the alcohol would have more electron density on the carbon compared to the electron density on the carbonyl carbon, because you can see that it can also have this resonance structure, making carbon electron more deficient. Okay, so in that case, if you have a higher electron density, if you're making a compound with a high electron density from a lower electron density, what do you call that process? Is it oxidation or reduction? It is reduction. So the more hydrogens you have in a compound, that process is called reduction. Okay, and then the opposite one would be oxidation, meaning alcohol goes to aldehyde, and then we can further oxidize aldehyde to carboxylic acid, that is oxidation. The carbon is losing electron density on the carbon, the more oxygen atoms attached to it. For example, let me go ahead and erase all this. And all of this information is given in this discussion and background. Okay, so read it and you'll understand more of these things. Okay, for example, let's see, you have the same aldehyde, and this goes to alcohol, CH2OH. Now you understand, going from aldehyde to alcohol is a reduction, and then the forward reaction, the backward reaction, going from alcohol to aldehyde is oxidation. The more oxygen content increases, hydrogen content decreases. Now let's say aldehyde goes to carboxylic acid. You make aldehyde to carboxylic acid. What do you think about the electron density of the carbon? Has the electron density increased or decreased? Electron density around the carbon decreased, because now the carboxylic acid has two oxygens. So the two oxygens being more electronegative, it decreases the electron density on the carbon. So carbon is losing, right? If you lose electrons, is it oxidation or reduction? It is oxidation. So the forward reaction, in this case aldehyde becoming carboxylic acid, is oxidation, and then the reverse reaction, whereas the carboxylic acid becoming an aldehyde, is a reduction reaction. Okay, and it also talks about in the discussion over here. Okay, you can see here, organic compound that has a carbon atom that has been reduced has generally obtained more hydrogen atoms. Hydrogen is less electronegative than carbon, so bonds to additional hydrogen atoms increase the electron density around the carbon atom. In contrast, when oxidation occurs in an organic molecule, a carbon atom loses hydrogen atoms or forms additional bonds to more electronegative elements such as oxygen or nitrogen. Okay. Okay, so now we're going to talk about the reaction that we are doing today. So what we're going to do is we're going to convert aldehyde functional group in vanillin to alcohol. Aldehydes always gives us a primary alcohol because it's a terminal carbonyl group, and ketone gives us a secondary alcohol. Excuse me. And we can also use, we have learned in the lecture many different types of reducing agents. We learnt about sodium borohydride, we learnt about lithium aluminum hydride, and we also learnt about the variation of sodium borohydride. Dibal-H is one thing, diisobutyl ammonium aluminum hydride, sorry, diisobutyl aluminum hydride, that's Dibal-H. And also we learnt about sodium cyanoborohydride, which is a milder version of sodium borohydride. Okay, but in this lab we are using sodium borohydride, which is more milder than lithium aluminum hydride. Lithium aluminum hydride can generate hydrogen gas if it exposed to water or alcoholic solvents, and it can also get fire. So we want to make sure no water molecules or alcohol in the presence, but we're not going to work with aluminum hydride, lithium aluminum hydride. Okay, but we're going to be using sodium borohydride, which is a mild reducing agent, much safe to use in the lab. And we're going to be using a freshly prepared solution of sodium borohydride in water or methanol, and that is going to be stable. It's not going to generate hydrogen gas, so we can work with it. Okay, so sodium borohydride is effective for the reduction in aldehydes or ketone, but we cannot use it to reduce like the esters or carboxylic acid or any other carbonyl compounds. And this is the main reaction that we're going to be dealing in this experiment. So we have vanillin. Vanillin is the structure. It has aldehyde functional group. It has an ether and alcohol. We're going to be doing this in water. We add sodium borohydride as our reducing agent, and at the end we will have vanillyl alcohol. Okay. Sodium borohydride, we're going to dissolve it in aqueous sodium hydroxide. It is necessary to use a basic solution. Why do we need a basic solution? Because vanillin also contains acidic phenol group. Do you see that? The alcohol group over here, not that one. Let me show you the alcohol. You can see that. That's a phenolic group. Over here, this OH group. If you have a neutral medium or yes, if you use a neutral reaction condition, so the sodium borohydride, H minus, sodium borohydride, hydride ion can react with the hydrogen of the phenol group. So then our sodium borohydride will not solely available to do the reduction. So there is a competing reaction. To avoid that, we always carry out this reaction in a basic medium such as sodium hydroxide. So what does a sodium hydroxide do? Instead of sodium borohydride doing this, when you add sodium hydroxide, our base sodium hydroxide is going to do this deprotonation and create this anion, phenate anion. So then your sodium borohydride is available to do the reduction. Okay, so that is the purpose that we are doing it in sodium hydroxide basic medium. The hydroxide present under the reaction condition will serve to deprotonate the phenol group. Okay, allowing the hydride to react selectively at the carbonyl carbon atom. Mechanism of the reduction is outlined below. So you can see how the reduction takes place. Sodium borohydride. So if you take one sodium borohydride, how many hydride ions are there? If you take one sodium borohydride, BH4. Borohydride is this one, right? There are 4 hydrides in one sodium borohydride molecule. Okay. So the borohydride, one of the hydride attack the carbonyl carbon, then the pi bond opens up, and then we create alkoxide anion. Also we have this phenate anion, and that is being done by sodium hydroxide. And after the first step is done, we completely reduce and create the alkoxide ion. In the second step, we are going to quench this with hydrochloric acid. So the acid will help to protonate the phenate ion. So we're going to be adding hydrochloric acid. Hydronium ion is the acid that is present. So that will give you the final product OH. Same thing over here. It also going to grab hydrogen or proton from hydrochloric acid. So that will give us the vanillyl alcohol. Okay. Notice that one molecule of borohydride contains 4 reactive BH bonds. In theory, one borohydride molecule should be able to reduce 4 alcohol molecules. At the end of the reaction, boric acid will be formed as a byproduct. And we also need to control the temperature of the reaction. We need to keep it slightly below the room temperature. So, hydride does not react significantly with the water solvent. And also at the end of the reaction, the water-soluble sodium salt of vanillyl alcohol will be present in the aqueous solution. Yes, like I mentioned before, the neutral vanillyl alcohol need to be recovered by acidifying the reaction mixture with HCl. Both the phenate ion as well as alkoxide ion will be protonated and will give us vanillyl alcohol. Acidification also quench any unreacted sodium borohydride. You will definitely notice bubbling as unreacted hydride react with protons from the acid to yield hydrogen gas. When you watch the virtual lab, you will see this. It's forming a white color foam. Okay. A bit of foaming at this stage is good as the foam provides a nucleus for the growth of the crystals of vanillyl alcohol. And like I said, it's a very nice, pleasant smell. The whole lab would be a smell like we have eaten vanilla ice cream or something in vanilla. Okay. And these are the properties of our reactants and the products. Vanillin molar mass is given, vanillyl alcohol molar mass given along with their melting points, sodium borohydride, 6 molar hydrochloric acid. Safety: sodium borohydride is basic and will decompose violently upon exposure to acid. So we want to make sure that we will not mix our sodium borohydride with any acid. Over time, it will decompose upon exposure to moisture in the air. So when we are keeping or storing, we normally keep our sodium borohydride in a desiccator to get rid of any moisture in the environment that it's stored. And also at the same time, if you right after you measure the amount of sodium borohydride that you need, you want to put the lid back on so the moisture in the air will not get inside the sodium borohydride and decompose it. And sometimes we have experienced that we had to throw away some of those sodium borohydride bottles in the lab because they are no longer functioning the way that we want, because it could be destroyed by the moisture in the air. And the procedure is given how you are going to perform the experiment. You will take Erlenmeyer flask. You can add 25 millimoles of vanillin. So 25 millimoles is 3.8 grams. Okay, and you're going to put 30 milliliters of 1 molar sodium hydroxide. And now you know the reason for adding the sodium hydroxide. The sodium hydroxide basically deprotonate the phenol hydrogen, okay, and make the phenate ion. And then you're going to let it stir until it completely dissolves. If it does not dissolve, you can add 5 more sodium hydroxide. And then after it completely dissolves, you're going to remove the flask from the stir plate, and you're going to put the reaction mixture in an ice bath, and we want to keep the temperature below 15 degrees Celsius. You can put a thermometer inside and monitor the temperature. It doesn't have to be at 0, it just needs to be below 15 degrees Celsius. And in a small separate beaker, you will see in the virtual lab that you are going to prepare, you're going to measure 12 millimoles, 0.450 gram. Okay, now look here, we are using 12 millimolar sample of sodium borohydride. What is the number of millimoles we took for vanillin? 25 millimoles. We are taking 12 millimoles of sodium borohydride. In terms of millimoles, the amount is going to be less than the vanillin, correct? And you're going to put that in sodium hydroxide. You add 60 milliliters of sodium hydroxide in a 10 milliliter beaker. You mix it. And then you stir. While you are stirring your reaction mixture, you're going to add this sodium borohydride to the flask. Over a 5-minute period, you're going to be adding it drop-wise. After you add it drop-wise, you're going to stir it. Continue to monitor the temperature of the water bath, maintaining a temperature close to 20 degrees. If it is too cool, what's going to happen? The reaction will proceed too slowly. If it is too warm, the product will not crystallize properly at the end. So we want to keep it around 20 degrees Celsius. Once all the sodium borohydride been added, we're going to let the reaction mixture to stir for another 30 minutes to complete the progress of the reaction. Okay. Once the 30 minutes done, we're going to be slowly adding 6 molar hydrochloric acid. We may need to add about 10 milliliters. Keeping the temperature again below 15 degrees Celsius. Keeping an ice bath, you're going to be adding hydrochloric acid. Now, what is the purpose of adding hydrochloric acid? We talk about it. It's going to give back us the vanillin alcohol. So after the 30 minutes, what you're going to be having is this compound that you are seeing here. So this is what you're going to be having before you add your hydrochloric acid. And then when you add hydrochloric acid, this anion, there are 2 anions in the vanillin alkoxide. So these will get protonated and give us vanillin alcohol. That's the purpose of adding hydrochloric acid. When you add hydrochloric acid, you will see that it start forming. And then you're going to let it crystallize, and after it forms the crystals, you're going to filter it under vacuum. Okay, and also you want to make sure after you add about 10 milliliters of hydrochloric acid, you put a pH paper inside and check to see if the pH is acidic enough. If not, you can add a little bit more. Okay, and then you're going to collect the vanillin alcohol by vacuum filtration. You're going to wash the crystals with cold water, store the product in a container, and then you're going to get the melting point and the mass of the vanillin alcohol. Okay, and you will see this procedure is being conducted in the virtual lab. Okay, what are the safety precautions for working with sodium borohydride? We talk about it. So what should be the safety? So we want to make sure that it is not exposure to the moisture. It's not exposure to any water, okay, or acid, because then it can destroy the sodium borohydride. So you have to be very careful about it. Okay. We need to make sure that the lid is always put on, so that way the environmental moisture will not get inside the sodium borohydride. What is the reaction conducted today considered? Why is the reaction conducted today considered a reduction? We talk about that also, right? Because a reduction is where you have more hydrogens on the carbon of interest, because hydrogen electron density is less compared to carbon. So the carbon can have more electron density on it. Okay, so the more electron density on carbon, meaning it has gained electrons, it is a reduction Oxidation is loss of electrons, reduction is gain of electrons. Our aldehyde has one oxygen and one hydrogen. Oxygen is a double bond, whereas in our product we have two hydrogens and one singly bonded oxygen. So the electron density of the product alcohol is more on the carbon than the electron density of the reactant carbonyl carbon. Okay. Dover reaction scheme showing the conversion of acetone into isopropanol using sodium borohydride in ethanol. Now you know what is acetone molecule look like. Acetone is this. Acetone, so you have to just draw the reaction scheme. Isopropanol using sodium borohydride, NaBH4, and your solvent is ethanol, ETOH. ET stand for ethyl group, ethanol. And then isopropanol. What is isopropanol? This is isopropanol. Now, do you think we need sodium hydroxide in this reaction? Do we have to do it in the base? For the experiment, we use sodium hydroxide. But do you think we need sodium hydroxide for the acetone reduction also? Excuse me. No, right? Why not? Because we don't have a phenol kind of alcohol group here. So we don't need to use sodium hydroxide. We can do it in ethanol. Remember, we use sodium hydroxide because we want to deprotonate the alcohol, which is the phenol in your starting material. Otherwise, the sodium borohydride would compete to do the same. Draw a mechanism that corresponds to the reaction scheme you drew above. You can do that, right? Because we already know the mechanism for the vanillin alcohol, vanillin forming vanillin alcohol. It's the same thing. So here you have this one, borohydride, B minus goes over here. O H, and in the second step you can acidify it, and this will grab a hydrogen to give you isopropanol, okay, which is same as this, okay. What is the limiting reactant in today's experiment? Explain. So today's experiment we had vanillin, okay. So vanillin is this molecule, and then with sodium borohydride we got vanillin alcohol, this, and we started with 25 millimoles of vanillin, and we used 12, was it 12.5 or 12 sodium borohydride? Let's look at 12 millimoles. See, 25 millimoles vanillin and 12 millimoles sodium borohydride. 12 millimoles. Now, which one is the limiting reactant? So, we learned in General Chemistry 1, limiting reactant would be the one that has the least number of moles. So, vanillin has 25 millimoles. Sodium borohydride, we use 12 millimoles. So, which one is going to be the limiting reactant? Sodium borohydride, because it has 12 millimoles. If sodium borohydride is the limiting reactant, then what's the number of millimoles of the product that you're going to form? According to the limiting reactant, the least number of moles, 12 millimoles, 12. So then our product also should be 12 millimoles. Is that correct? Our limiting reactant is sodium borohydride. Everybody agree that it is correct? Or you all disagree with that? Disagree? Okay, great. So why? Tell me why. Okay, great. So you gave me the correct answer. So what you said was, let's see. Now, even though we use 12 millimoles of sodium hydride, sodium borohydride, in one sodium borohydride, how many reducible hydrides do we have? Now, this is your sodium borohydride. Sodium, we don't need sodium. Let's only use borohydride. So borohydride, if you take one sodium borohydride, how many hydrides are available for it to carry out the reduction? There are 4. So all of these hydrides are equally capable of reducing a molecule. So one sodium borohydride molecule, there are 4 hydride ions. So if you have 12 millimoles of sodium borohydride, how many millimoles of hydrides ions are available? 12 times 4, 48 millimoles. So you were thinking the same, correct? So there are 48 millimoles, even though we use 12 millimoles. Now, which one do you think is the limiting reactant? Do you still consider sodium borohydride as your limiting reactant? No, because now we have 48 millimoles of hydride ions that could be reduced aldehyde carbonyl carbon. So our limiting reactant is going to be then vanillyl alcohol. If that's the least number of millimoles out of the reactants, so then the amount of the product also going to be 25 millimoles. Okay, so explain that in that space provided. Now you know how to explain. Determine the theoretical yield and percent yield for the reaction. Now that you know the amount of millimoles that can be formed, and in the previous experiments we learned how to calculate the theoretical yield. The number of millimoles, 25 millimoles of vanillyl alcohol. Okay, and then you can convert this into moles. That's going to be 25 into 10 to the negative 3 moles. And then we know how to convert moles to grams by using the molar mass of vanillyl alcohol. We have done that one before, so you should be able to do it. So we have to find out the theoretical yield. It's going to be 25 into 10 to the negative 3 moles of vanillyl alcohol. So 1 mole vanillyl alcohol is the molar mass of vanillyl alcohol, which you can find from here in your data table, not the data table of properties. Vanillyl alcohol 154.2. So you will multiply that by 154.2. 154.2 grams. This will give you the theoretical yield. Okay, and remember the percent yield is actual yield, which you're gonna find from your virtual lab, and then you divide it by this theoretical yield times 100 will give you the percent yield. Okay, so I know you can calculate that. In this experiment, the identity of the product will be confirmed by melting point. Why does it make sense that the product has a higher melting point than the reactant? Consider intermolecular forces. So what are our melting points? Vanillin melting point 81 to 83, and then the vanillyl alcohol 130. So vanillyl alcohol, you can see, has a higher melting point. So what should be the reason for that? What's the reason? So vanillin is this guy. You have aldehyde, and vanillyl alcohol is this. So why do you think this is 88, this is 113 melting point? Consider the intermolecular forces. What are the intermolecular forces that we have in these molecules? What is the very basic one? That all kinds of atoms and compounds and molecules going to have the very weak but present in everywhere, which is van der Waals forces or London dispersion forces. Dispersion forces are everywhere. That's the most common one to all. And in addition to that, if you have a polar molecule, you can have a dipole-dipole interactions. Okay? And then you can also have hydrogen bonds if you have hydrogen atoms in the molecule, that the hydrogen connected to small highly electron denser atoms like NOF, NOF, nitrogen, oxygen, fluorine. When the hydrogen connected to oxygen, nitrogen or fluorine, they are special kind of intermolecular interactions. We call them as hydrogen bonds. Okay, so in vanillyl alcohol, since there are two alcohol groups, this can have more hydrogen bonds compared to this. Aldehyde also has hydrogen bonds because it has a hydrogen connected to oxygen. Right? Now, do you think any hydrogen bonds here? CH3. There are hydrogens right there. Okay, another hydrogen on this one. But those hydrogens are connected to carbon, so that cannot form any hydrogen bonds. And the only thing that can form hydrogen bonds in the vanillin molecule is this OH group. Okay, whereas alcohol, vanillyl alcohol, you can participate hydrogen bonding with this hydrogen bonded to oxygen as well as this. Okay, now let's look at how we can get some hydrogen bonds. Let's say we have a molecule like this, CH2 OH, and then you have your OH here, and then we can have our OMeO group, and then you can have another molecule where you can form a hydrogen bond with this one, hydrogen, oxygen, CH2 OH CH3 right there. So you can have another hydrogen bond over here, this hydrogen and oxygen, because oxygen has two lone pairs. So those can participate in bonding with the hydrogen, and this oxygen can also participate in hydrogen bonding. This also oxygen can also participate in hydrogen bonding with another alcohol molecules, hydrogen, oxygen, and then the rest of the molecule. So you can see there is a chain reaction, a chain of hydrogen bonds in this molecule. Okay, so as a result, when you have two alcohol groups, you can see how the hydrogen bond take place. And the more hydrogen bonds we have in a molecule, it increases. So that benzene ring does not look good. It increases the boiling point and also the melting point. We were looking at the melting point, not the boiling point, right? Because they were crystals. Okay, so that is the hydrogen bonds. Whereas in the aldehyde starting vanillin, we have only one alcohol group. It can also form hydrogen bonds, but not as many with the two alcohol groups, which is our vanillyl alcohol. Okay, all right then, I think that's about it.